This is our first module of the class. It's about enterprise campus architectures. Basically, we'll talk about design guidelines for a multi-layer hierarchical network. We're still talking about campus and we're still talking about switching. The module also includes some of the operational implementations and operational guidelines to deploy this type of architecture. In this lesson, we'll talk about some of the existing models that guide your design decisions. This is very important. We should start with a model that tells us what to do and what the objectives are. Some of the models are listed here. One of them is Cisco's own service-oriented network architecture. This is probably being replaced and expanded into something called Cisco borderless network architecture. In any case, both relate to a hierarchical model in which we have a base layer of network infrastructure services. This is not yet the equipment and product layer. This is still viewed from the perspective of a campus network in which you have the campus but also have branches and data centers providing services. Of course, the products, the network fabric and the network infrastructure sits below that layer, and it includes routers, switches, and the rest of the architecture. Now, the important thing here is that we're looking at it from the perspective of a places in the network approach, in which design guidelines depend on where you are implementing that switch, where you are deploying that router, and where you are deploying the pieces of equipment. So it'll be different to have a switch on a campus network core than having a switch on a branch LAN. And so, let alone talk about a switch for a teleworking architecture, in which it's just a collapsed set of services in perhaps one or a couple of devices. So the network fabric should be there, and it's what we're used to. Routers, switches, and other devices. Of course, again, viewed from the perspective of a places in the network approach. Places in the network. Now, network services sit on top of that. Our interactive services layer is the one providing security services, is the one providing mobility, storage, and those services that are universal across the network fabric. In other words, here's where we see firewalling services, for instance, in terms of security. Where can I deploy a firewall? Well, physically, it could be in the form of an iOS firewall in a router, or perhaps a layer 3 switch, or it could be a firewall appliance, or even a firewall virtual machine sitting on a VMware server. So this architecture talks about services as decoupled from the physical infrastructure, and we've been seeing that in the Cisco architecture for years. The important thing here is, again, that we now combine that with a places in the network approach in which my security services not only have several deployment options from the physical or virtual perspective, but also different functional perspectives depending on which place in the network we deploy it. Now, of course, we're talking about enterprise networks, and those run business applications. And so our last layer is that of business functions, which decouples the services of the network from the actual functional perspective of it. And so here we have communications, IP communications services, and we have contact center type applications, video delivery, and content delivery, e-learning, etc. So applications take advantage of network services that are decoupled from the physical layout and physical architecture in the form of a network places in the network model. So that's what SONA is all about. And of course, multiple benefits to that. Scalability, because you can now build or expand your network fabric without touching or without having a huge impact on the network services that you provide on top of that fabric. Your functionality is improved because now you're talking about business services and business applications, which should be able to coexist with any architecture, services and network architecture. Performance is improved. Manageability is there in any of these models because for each layer you have a network management model or component, infrastructure management, but also services management, application delivery, and so on. And so again, each layer will have its own management component, and that's how you make the layers interact as well. So several benefits both from a technical and business standpoint. These models also coexist with other models more on the technical side, for instance, a hierarchical model or hierarchical network architecture. What we're trying to say here is that for each place in the network that we mentioned earlier, for instance, a campus network, you could design that particular component following a layered approach in which you have core, distribution, and access layers that correspond to different functions at the network for the network component for that particular place in the network. And so this is similar to perhaps what we see in the highway, right? We don't have all of the cities in the US connected by a single or by multiple streets or highways. We have a core of expressways connecting different regions and areas of the country, and then branching out into smaller interstate or regional expressways, regional highways, and then branching out into cities, branching out into streets. Same thing here, we're going to see for each place in the network with different levels of complexity, of course, we'll see the components of a core or trunk component or area, distribution which is the one aggregating following our analogy, aggregating, for instance, multiple cities into one big regional expressway, for instance. And then the access layer, which is represented in our analogy by the multiple cities and the streets on those cities. So it's hierarchical in nature, and you'll see something like this, right, where perhaps the core of the network aggregates or connects multiple branch offices, which in turn aggregate multiple buildings. And each layer will have its own functional and design guidelines. So for instance, in a campus architecture, we have campus core, campus distribution, campus access. The importance of this is that we can segregate the functions, and we can design thinking of the functions of each layer in particular. And of course, all of the layers are going to be interrelated and integrated. Let me give you an example of that. In the access layer, for instance, if I plan for the access layer, I'll probably think of convergence of voice, wireless, and data. Here's where I will probably provide power over Ethernet services and connectivity for different types of devices. For instance, smartphones, anywhere from smartphones to video cameras, IP video cameras, and I should provide that type of variety in my access layer so that multiple types of devices can connect. Now, since multiple devices can connect, I should also focus on security services that tend to push our security controls to the boundaries of the network so that the malicious or non-malicious or unwanted attackers can be stopped at the network edge, right when they connect. So security services is probably something you'll see as a highlighted function as part of the access layer, in addition to that variety of topologies and technologies that allow multiple types of devices to connect. So that's just two examples of the focus of the access layer. And again, the access layer can sit in different places of the network. So you'll have a WAN access layer, but also a LAN access layer. The important thing is that you would focus on a certain set of design guidelines and be able to design that component thinking of those guidelines and making sure that those settings or characteristics of that layer are implemented correctly. So the other example is a distribution layer. For instance, in a campus, this is the one aggregating and summarizing uplinks coming from the access layer. So again, it's like a regional highway as opposed to a city highway. It's a turnpike or interstate instead, as opposed to a city loop, for instance. So, but this is one that aggregates multiple access layers. This is the one that allows you to build a distribution layer and then expand it or scale it moving horizontally, right? For instance, it's like having the interstate and then hanging off of that interstate multiple city exits or city distribution centers. So I can expand to the right. I can connect multiple access layer blocks to the same distribution layer. Its job is to aggregate the access layer. And then taking advantage of that, you will probably and most likely implement policies and do the whole policy-based approach to aggregation. In other words, here's where you will probably implement a firewall. Here's where you will probably start or initiate the implementation of quality of service policies to provide different types of access and different quality different service level agreements to different access blocks coming from the access layer. So again, just a handful of examples of what the distribution layer should do and highlighting the main design guidelines for that particular layer. We can focus on those guidelines. We can focus on providing aggregation, security, isolating problems, and creating that type of fault or isolation domains. Core, of course, has a very distinct job, which is fast, fast, fast. We need to provide fast switching, high-speed backbone to aggregate multiple distribution blocks. So it's a next level up that should have a very distinct focus: reliability, redundancy, fast convergence. So we should not have, and we will probably not see different service-oriented approach to the core layer. We will not see, for instance, access control too much in the way of access control lists. You will not see too much in the way of specific quality of service. We should provide a fast architecture for forwarding and switching of packets. So again, that's a distinct focus of the core layer. It doesn't mean that we're going to have that as the only design guideline, but in general terms, we can focus on providing those services and leave the rest to the distribution and access layers. Of course, there are different exceptions to each rule. And so is a core layer really needed? Well, it depends on the places in the network approach that we've been mentioning. In the case of a campus network, where in this example, for instance, multiple buildings, 1, 2, 3, and 4 buildings, connect to communicate or provide services to users on those buildings. If we don't provide a distinct core layer in the form of separate devices or at least separate functions, then we can see how the complexity starts building up. For instance, for the first building, all I have to do is create my distribution block, but then for the second building there, I will need at least 4 new links to create the illusion or the reality, actually, of a highly redundant core network. 4 new links to connect those 2 new additional switches to the existing core, which is the existing building. So what I'm trying to say here is that in this example, we don't have a core network in the form of specific devices. What we have is what they call a collapsed core, in which the core function is built into and integrated into the distribution layer switches. So the whole aggregation, the whole provision of a highly redundant fast switching network is collapsed into distribution layer switches. And again, you can see how the complexity starts building up. For the third block, I'm going to need 8 new links if I don't have a core. And then for the fourth building, I'm going to need 12 new links for 24 links total. And not only do I have additional complexity in the form of physical connections, but also additional logical complexity in the form of a lot more routing peering, a lot more in the way of routing protocol overhead. It is completely different if I provide that turnpike between the different buildings, so to speak. Again, it's the same thing. It's similar to the highway infrastructure. We don't have different or one expressway between each city of the state. We have perhaps the big highway that connects them all. Same thing with the core. We will be able to provide more predictability and more scalability. The example as compared to the previous one is for each building block, we know that we need to connect each distribution switch to the 2 core switches in this example. And we want redundancy. If we want redundancy, then we probably want multiple links between them. But the point is, we have predictability. For each building block, we're not going to add a lot more physical connections. We're going to add perhaps 2 or 4, depending on the level of redundancy that we want. And again, it's like a big interstate or turnpike type highway. If I connect to the highway, I'm connecting to the rest of the state. Same thing here. If I connect to the core from each building distribution, then I'm connected to the rest of the network. So less routing complexity, less physical cabling, and more hierarchical and clean network architecture. Let's take a look at some other examples now.